Hi, and welcome back. This series of lectures is going to deal with the material in Chapter 2. Now, if you remember our discussion about Chapter 1, I had mentioned that it primarily deals with what we consider to be the macroscopic measurables, the macroscopic world. So we know things like, pressure, temperature, volume, mass. These are all things that are measurable very easily in the lab. Okay, so easily measurable, and they make sense to us, because concepts like pressure, force over area, and temperature, volume, and mass are all things that we more or less can directly interact with. Now, in this chapter, I'm going to start to introduce the microscopic things. So, primarily, what I'm going to talk about is something called the kinetic theory of heat or the kinetic theory of gas. It's more or less the same thing in this particular case. And we're going to get to that here in a moment. However, in order to get there, and the just as a forewarning, the guts of this chapter are going to consider gases and not so much solids and liquids. But before I get there, what I'd like to do is to talk about some, we'll say, quantitative experiments that have been done and what they say about these sorts of quantities right here. So before I get there, though, what I'd like to talk about are two basic types of idealized containers that we see used when dealing with gases. So a container is something that you put your gas in when you're looking at it, you're examining its properties. So the two idealized ones are uh, iced containers. The first one is something that holds your gas at a constant volume. So a good example of this would be, some sort of gas cylinder, like for example, a scuba tank, and what have you. Now, the second type of container is one that holds it at a constant pressure. Now, in order to explain what types of containers do this, what I'd like to do is to sort of remind you about what pressure is. Now, remember, pressure is force exerted over an area. So, I'd like you to consider a balloon. So let's pretend that this is sort of like this is your balloon. It's a three-dimensional object. So you have surface area here, okay, that surrounds the whole thing, obviously. And we're gonna pretend that this balloon here is infinitesimally thin. Okay, so this is a very, very thin balloon. So what that means is the area on the inside and the area on the outside are the same. Okay. So imagine blowing air into this balloon and letting it expand. So neglecting the elasticity of the balloon and the fact that there is going to be a small amount of force there. This balloon, as you blow air into it, is going to expand. And the air on the inside, if you remember our discussion, in the last series of lectures, we know it's moving around, colliding against the walls of the interior of this thing. And as a consequence, you have a pressure or a force being exerted on the inside, a force being exerted over the area. So there's a pressure on the inside. Now, this thing is going to expand as you blow air into it. And when you stop blowing air into it, it's going to stop. And what that means is that since the surface of the balloon isn't expanding or contracting at that point, that means that whatever forces sit on the outside that are acting on the outside like this against it, they're going to have to be balanced out by the forces on the inside. So if you think of that force being applied over the area here, that means that the pressure on the outside is the same as the pressure on the inside. So balloons are examples of things that hold gases at constant pressure if you can neglect, again, their thickness and the elasticity, okay, which is negligible in many cases. So a balloon is a good example of this. All right. So if you think about a gas, gases can have pressure, they have volume, they have temperature, and there's also an amount, okay, a mass, we'll say. So if you think about that, the mass itself, if we treat this gas as simply as we possibly can, if we think of the atoms or molecules that make our gas up as being unique, or not unique, but identical, if you think of them as not really interacting with each other at all, the only thing that they're able to interact with would be the walls of the container that they're in, then whatever mass that you have here is going to be proportional to the number of atoms that you have on the inside. So many times, instead of dealing with mass, we find it preferable to deal with the number of molecules, okay, or atoms. Now, from a chemistry standpoint, instead of dealing with the number of atoms directly, what we do is we scale the number of atoms by a number called Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd atoms. So in doing so, what you get is typically defined as lowercase n, and it's what's called the number of moles. And it's just a convenient way to sort of abbreviate the number of particles that you have, because, 10 to the 23rd of anything is an enormous amount. And 1 mole of material visibly is not very much typically. So it's easy to sort of scale this. You can think of the number of moles as sort of analogous to, say, kilograms for the number of particles. So, what that means is, again, your mass is also, linearly proportional to the number of moles, if you want to think of it like that. So sometimes we use the number of atoms, sometimes we use the number of moles. Quite honestly, the number of moles is typically, or predominantly rather, used in chemistry, although we are going to be using it a little bit today as well. And the number of atoms is typically used in physics. We just find it easier to work with. So that said, I would like to take these two idealized containers and use them to examine how pressure, temperature, volume, and I'll start with the number of atoms sort of relate to each other. So we'll start with the fixed volume. So, like I said, a fixed volume container would be something like an acetylene tank, like for gas, or a scuba tank, something that in general does not expand as you take and you put material in it. So, if you think about all of the stuff that we have here, these four thermodynamic variables, pressure, volume, temperature, and number of atoms, with volume being held fixed, if I took my container and I increased the number of particles in it, what I would discover is that the number of particles inside that container, or the amount, would be directly related to the pressure that I see generated by them within the container. Now, this should make sense if you think about what pressure is. So if you think about the walls of your container, and we'll say here's one right here, you have this random motion of all these little atoms and molecules that sit within it. And on occasion, you have them hit a wall of the container and bounce off. Now, so what you've had here is you've had this gas particle experience a change in momentum. And I'm going to write this as P vector to differentiate it between, pressure and momentum here. Okay. So if there's a change in momentum, we know from our discussion in university physics 1 that means that there was a force applied by, this container wall on the particle. Well, as per Newton's third law, if the wall of the container pushes on the particle pushes on the wall of the container, so that there's a small amount of force applied here by this one particle. Now, this container has an area, so you have a force over area, which is a pressure just by this one collision. Now, the total pressure is what you get when you add up all of the collisions on the inside. So if I were to say double the number of particles that I have on the inside, presuming they're not interacting with each other, that means that you would have twice as many collisions. If you have twice as many collisions, that means your pressure is going to double as well. So in a fixed volume container, there is a linear relationship between the number of particles that you have on the inside of your container and the pressure. And that's entirely a consequence, of the number of collisions that are happening. Now, not only that, I can look at the relationship, we'll say, between temperature and pressure. So, temperature, we know qualitatively, we're going to see it quantitatively here in a moment, is related to the kinetic energy, or the average kinetic energy of the atoms and molecules that make something up. But we also know that there's a relationship between kinetic energy and momentum. It's p squared over 2m. Okay. So what that means is that there is a relationship between pressure and temperature. Remember, pressure is a consequence of collision. You have changes in momentum that occur. So when you increase the temperature of something, you're increasing the kinetic energy. As a consequence, you're increasing the momentum they have. And when they hit the walls of the container, they hit harder. So as a consequence, there is a relationship between temperature and pressure. And what you see when you actually do the experiment is that, again, it's a linear relationship. So we have this linear relationship between changes in the number of particles in the inside and pressure, or changes in temperature and pressure. Now, next I'd like to consider a container that has a constant pressure. So in a container that has constant pressure, what that means is that the volume can change, but the pressure is held fixed. So again, let's pretend that I double the amount of material that I have inside my container. Well, if I double the amount of material, what I've done is to cause the volume to double as well. So again, there's a linear relationship between the number of particles and the volume. The more particles, the more volume. Likewise, if I increase the temperature, what I'll notice is, because of the impacts causing the balloon to expand, that I also increase the volume as well. Now, empirically, if you do this in a lab, you'll see that it's a linear relationship. So what I have here are a bunch of relationships between the number of particles that something has, the temperature, the pressure, and the volume. And I can group this up the following way. We say typically P times V is proportional to N times T. Now, this is where you see the difference between chemistry and physics. At least one difference. So we know when we have linear relationships like this, any sort of proportionality, we put an equal sign and we put a constant. In physics, it's usually written this way. PV is equal to N times K sub B times T. This is called Boltzmann's constant. And it has a value of, let me see here, 1.38 times 10 to the minus 23rd. Joules per Kelvin. Now, in chemistry, the same equation is written the following way. Instead of using, again, the number of atoms, we use the number of moles. Little n, R times T. Now, R is the ideal gas law constant, and it has a value of about 8.31 joules per mole Kelvin. Now, if you compare this equation to this equation, we have a relationship between the number of atoms and the number of moles, and it's basically through the Boltzmann constant and the ideal gas constant here. So you can also write down that N times K sub B is equal to the number of moles times the ideal gas law constant. So this is something that you might want to star in your notes. This is important right here, and this is also important right here as well. Now, so that said, this type of equation is called a state equation. And state equations tell you the relationship between several variables. So really what we have here are four variables that could change, but the way they change has to preserve this relationship right here. Now, this particular, both of these equations, these particular set of equations, this is called the ideal gas law. And under the ideal gas law, we make a handful of assumptions. The first assumption is this, that the particles of gas are identical. Okay. And we also assume the particles of gas do not interact. And we also assume that they have no real size. They have masses, but physically don't have sizes. Now, again, this is the ideal gas law, right? And what that means is that for basically all of the gases that you see on the periodic table, all of the molecular gases that you see out there, you treat them all identically, since you don't have to take into account the fact that they have different masses and what have you. There's no mass in these equations, and this is a really good first order approximation to the behavior of a gas. Now, that said, what I'd like to do now is to define something, and it's called standard temperature and pressure. Now, many experiments are done at standard temperature and pressure. It's typically abbreviated as STP. Okay, and in the physics units, if you will, standard temperature and pressure is this: your pressure is 1.01 times 10 to the 5th pascals, and your temperature is 273 Kelvin. Now, 1.01 times 10 to the 5th pascals, if you've had chemistry, is also called 1 atmosphere. It would be the pressure due to the Earth's atmosphere sitting above you at sea level. Okay, so these are fully equivalent to each other, but in physics, we want to use this unless otherwise specified. 273 Kelvin should look familiar to you as well from last series of lectures. This is 0 degrees Celsius, so it's the freezing of the melting point of water. So, like I said, if you were to say do a problem and the problem mentions that your gas is at standard temperature and pressure, this is what they're talking about. Speaking of which, we can do an example. What is the volume in liters occupied by 1 mole of air at standard temperature and pressure? So what we're given here is that we have 1 mole of air. We're going to assume that this is exact. I know it's not stated as exact, but there's a reason for this. And again, for those of you that have chemistry or have had chemistry, you'll see what I'm talking about. Now, we want the volume in liters, but we're also given that the air sits at standard temperature and pressure, which means that our pressure is 1.01 times 10 to the 5th pascals. That is implied by standard temperature and pressure. We also know that our temperature is at 273 Kelvin. Now we're trying to find the volume, but we want it in liters. As given, it's going to give it to us in MKS units. So your volume will be in cubic meters. So the version of the ideal gas law that I'd like to use for this particular one is going to be this one, the chemistry one, and that's because we're given number of moles. So here our state equation is PV is equal to N times R times T. We're trying to find the volume. The volume is just nRT divided by P. We have 1 mole. Our ideal gas constant here is 8.31 joules per mole Kelvin. Our temperature is 273 Kelvin. And the pressure is 1.01 times 10 to the 5th pascals. So let me put this into my calculator here. Excuse me. Let's see here. 931 times 273. Oops. 73, there we go. Divided by 1.01 times 10 to the 5th pascals. And that is 0.0225 cubic meters. Now, the relationship between liters and cubic meters is the following. There are 1,000 liters in 1 cubic meter. So if I were to convert this to liters, noting the fact that there is 1,000 liters for every 1 cubic meter, this is the same thing as 22.5 liters. And if you've had chemistry, that should look very familiar to you, because that's one of the things that they tell you at the beginning is that 1 mole of a gas at standard temperature and pressure occupies 22.5 liters. Now, let's do a more complicated example. What is the density of Venus's atmosphere at sea level? Now, in order to do this, we need to look up some information about Venus. For example, if you look at what the surface temperature is, it's about 470 degrees Celsius. The atmosphere of Venus is incredibly dense, so dense that the pressure at sea level is 93 bar. Now, a bar is another measurement for pressure. For reference, 1 bar is equal to 1 times 10 to the 5th pascals. Okay, so when you say it's 93 bar, you mean it's 93 times 10 to the 5th pascals. So what that means is if you think of the Earth's atmosphere as being 1.01 times 10 to the 5th pascals, this is approximately 93 times more pressure on top of you, which would not be a pleasant experience. Now, if we're going to find the density, you're talking about the actual mass density, which we need to know something about the composition of Venus's atmosphere. And it turns out that Venus's atmosphere is about 96.5 carbon dioxide. It's also about 3.5% nitrogen. Now, I know you're probably looking at this and you're saying, okay, well, obviously it's more than just CO2 and nitrogen. And there are other things in Venus's atmosphere. For example, sulfur dioxide is one of the most predominant ones, but there's so little of it that it sits out here a couple decimal places beyond. Okay. So just like the Earth's atmosphere is primarily, nitrogen and oxygen. Okay, there are other trace elements there, but we're going to disregard them because overall they don't make an appreciable change to the density that we're looking for. Now, so this is what we've been given. All right, we're going to need to do some conversions. Like I said, this is the same thing as 93 times 10 to the 5th pascals. Now, we work in Kelvin. We don't work in degrees Celsius because we're dealing with a temperature and not a change in temperature. So to go from Celsius to Kelvin, all you do is add 273. So 470 plus 273 ends up being 743. Now, we want to find the density. But what is density? So density, we know, is just the total amount of matter occupying the volume. Okay. Now, if you look at the ideal gas law, and the one I want to use here is going to be the physics version. The physics version says PV is equal to N times K sub B times T. I can massage this into something that looks a lot like the density, but instead of it being mass density, it would be number density. But thankfully, I have the percentages. I have the percentages of the things that go into the atmosphere. So I should be able to use that and the mass of each one of these molecules to help find a density. And I'll show you how that works here in a moment. So what I want to do is to get it into a form that looks something like this, which means I need to divide both sides by V and also both sides by K sub B and T. Now, when I do that, I have N over V, and that's equal to P over K sub B times T. Now, if I were to multiply this by the mass of one atmosphere particle, we'll say, and I have this many of them in there, then I should be able to find the density. The problem is that I don't have one unique type of molecule. I have two. But thankfully, I know that from a mass percentage standpoint, about 96.5% of them are CO2, and about 3.5% of them are N2. Now, I need to find the mass of one CO2 molecule and also the mass of a nitrogen molecule as well. Now, thankfully, I can actually figure that out. We know, for example, if you were to look up on a periodic table, that carbon has a mass of 12.01 atomic mass units. We also know that oxygen has a mass of 15.999 atomic mass units. We also know that nitrogen has a mass of 14.0067 atomic mass units. Now, what's an atomic mass unit? Well, it's the approximate mass of a proton. U is equal to 1.66 times 10 to the minus 27th kilograms. Okay? So, for example, the mass of CO2 would be 1 carbon and 2 oxygens. So it would be the mass of carbon plus the mass of 2 oxygens. Now, nitrogen is molecular as a gas. Okay? So here, if I add these up, it's going to be 12.01 U plus 2 times 15.999 U. Now, if you put this into your calculator, I get 15.999, about 44.008 U. Now, for nitrogen, that's going to be 2 times 14.0067. $28.0134. Okay. Now, so what that means is the overall mass, which is a consequence of taking into account the different components in the atmosphere for one particle of atmosphere, would be about 96.5% this and 3.5% this, or 0.965 times 44.008 U plus 0.035 times 28.0134 U, or 0.96 times, or 0.965 rather, 44.008 plus 0.035 times 28.0134. So, this ends up being about 43.4482 atomic mass units. Now, let's not forget that one atomic mass unit is this. So this is our mass, okay? This is the average mass of a atmosphere particle, if you want to think of it like that. So, the density here is going to be what you get when you take that mass and you multiply it against N over V, which would be what you get when you take that mass and you multiply it by the pressure, you divide it by Boltzmann's constant in T. Okay? So, here, that's 43.4482 atomic mass units, noting the fact that one atomic mass unit is 1.66 times 10 to the minus 27th kilograms. The pressure is 93 bar, or 93 times 10 to the 5th pascals. Boltzmann's constant is 1.38 times 10 to the minus 23rd joules per Kelvin. and our temperature is 743 Kelvin. So I get, let's see, 43.4482 times 1.66 times 10 to the minus 27th times 93 times 10 to the 5th. Then I got to divide that by 1.38 times 10 to the minus 23rd. And then multiply that by 743. And I get 65.42 about. Kilograms per cubic meter. Now, for reference, at sea level and at standard temperature and pressure, the Earth's atmospheric density is about 1.2. So what that means is that if I were to divide that by 1.2, is that you're looking at a density that's about 54 and a half times as dense as the Earth's atmosphere. So pretty cool. All right. So just a few examples showing you how to use the ideal gas law. Now, what I want to do is to use the ideal gas law to help describe the relationship between temperature and energy. So what I want you to think about is a cube, a container, okay? Like this. And let me sort of complete the back side there. Actually, maybe I don't need to. Well, yeah, I really should, I guess, just to be consistent. We're going to pretend that this is a true cube and that all the sides have the same length here. There you go. So, so here's our cube right here. Each side has an area of A. The sides are L by L by L. Okay, so this is the volume. The volume would be L by L by L. The area of one side would be L squared. Okay. Now, inside this container, I want you to think about a bunch of gas particles. And what we're going to do is we're going to look at one that starts on the absolute back side, the back wall. And it travels this way to collide against the wall over here. Okay. So what I'm going to do here is to move away from this. And now we're going to just look at the two walls and the bottom, sort of side by side, something like that. So here's one wall. Here's another wall right here. And then here's the back wall, just to give us a backdrop, if you will. And so what we have here is our gas particle coming along and hitting the wall of the container over here. Now, if you remember way back when in University Physics 1, when I talked about collisions, through conservation of momentum and what have you, one of the things I mentioned was that, if you have an object that has a lot of mass, we'll say that sits at the origin and that it's at rest, and you collide it with something that has very little mass, what happens is the thing that's got a bunch of mass, it recoils incredibly slowly, but the smaller mass thing bounces off the other way. Now, if you look at what happens when the big massed object has a mass that's much, 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 much greater than the small one, what you'll discover is that the small one, when it bounces off uh, with a speed that's exactly as the speed that it had when it came in. It basically just reverses direction. Now, since this has a little bit of up tracking to it, when it bounces off with the same x and y components. It's just the direction of the x component has changed. So really, it's this right here. It's this x component part. If I call this an x and I call this y, it's this x component part right here that would be doing any pushing into the side over here. Okay, so what I'd like to do is to if we call again this L and this L right here, noting the fact that each wall has an area of A. If I look at this, if I look at the change in momentum that this thing experiences, okay, if I just look at the change in momentum of the particle, okay, so the initial momentum is to the right, the final momentum is to the left. We're going to assume 2D motion just for the moment. We're going to extend it to 3D in a second, but it's going to have a Vx part and there'll be a Vy part. Before and after the collision, the Vy parts are going to be the same, which means that if I look at the change in momentum in the y direction, it's going to be 0 because it continues to drift up y. However, if you look at what happens in x, the final momentum is to the left, the initial momentum is to the right. Now we know change in means final minus initial, which means that your change in the momentum along the x direction would be minus mvx minus mvx. Final, which is to the left, minus the initial, which was to the right, but they're identical in magnitudes because the mass of the wall is so much greater than that of an individual particle. So, excuse me, the change in momentum here is minus 2mvx. The force, and again, this is the change in momentum that the particle experiences. Now, what I want to do ultimately is to relate this to pressure. Pressure is going to be the force that the particle exerts on the wall. This is related to the force that the wall exerts on the particle. But we know, as per Newton's third law, if object A exerts a force on object B, B exerts the same force back on A, just in the opposite direction. And if you take the opposite of this, you end up with a positive. So this right here is wall on particle. And particle on wall which is what we want, is the positive version. That's the opposite direction from Newton's third law. So that force of just this one single particle right here would be the change in momentum over the change in time. Okay, that's the collision time. Now, the collision time, since we're just looking at this as being our initial velocity and this being our final velocity, this is our starting position, this is our final position. The collision time here, you can relate to the velocity the following way. We know at constant speeds, distance is equal to velocity times time. If I start here and then end up back here, the total distance would be 2L. So this right here really is the collision time. So what that means is that this force I can write, and this again is, to be clear, just due to one particle. I can write it as delta px over delta t, or 2m Vx over, and if I solve for delta t over here, 2L over V sub x. Now you'll notice the 2's cancel. You'll also notice that you have a 1 over Vx here, which flips up and becomes a Vx squared. Oh, now this is actually looking close. This looks a lot like kinetic energy. It's not quite there yet. This is just in the x. If you want the full kinetic energy, you'd have to consider the y and the z part, which we're going to get to here in a moment. Okay. Now, so that said, though, we can talk about the pressure. The pressure of just this one collision would be the force into the wall, that's the x part, divided by the area. The area is this entire wall. So this would be mvx squared over L times A, but A is just L times L. And if you go up here, L times L times L is the volume. Now, so this is just one particle. What I'd like to do is to add up all of the pressure. Okay? So if I add up all of the collisions on the inside of this container, if I sum up the collisions from I is equal to 1 to however many particles I have on the inside, this is going to give me the total pressure on the inside. Now, we're going to assume that all of our little particles are identical, which means that if I look at this equation over here, which is what we're summing, the only thing that could change would be the velocities. Okay. Now, so before I go any further, what I'd like to point out is the following. The motions of the atoms and molecules that make something up are random. Now, how do we know that? Well, assuming there's no external influence on things. If you were to, say, take a hot cup of coffee, okay, and sit it on a table like this. Let's just pretend for a moment that the collisions of the little coffee and water molecules in here that are really hot on the walls of this thing were not completely random. Let's pretend that there were more collisions on this side than there were on this side. Well, if that was the case, over time, this thing would slowly move to the right. We don't see that. What we see is that if we take this thing, we sit it on the table, it stays where it's at. And what that means is that the average amount of force exerted by collisions on this side and the average amount of force exerted by collisions on this side, they have to be the same. The sum of the forces on the object overall equals to 0. It stays there. And that's true for the motions of the gas particles inside here. In the absence of any sort of biasing thing on the outside, these particles' motion should be completely random. So what that means is the following. If I were to look at the average speed, we're going to square it to make it positive in the x direction. And if I were to look at the average one in the y direction, and I were to look at the average one in the z direction, overall, okay, these should all be the same. You have the same amount of motion along x as you do along y as you do along z. So if these are all the same, we know Vx squared plus Vy squared plus Vz squared would equal to v squared. What that means is that Vx, Vy, and Vz are all 1/3 of just the average speed. So I can write this as 1/3 v squared sub I. The following way. Now, instead of summing over just speeds in the x direction, I'm summing over speeds on average in general. Okay? Now, so here's what we have so far. Whoops, let me go to my little, okay. So I have P is equal to 1/3 M over V times the sum from I is equal to 1 to N of V sub I squared. Now, I want you to think about what an average is. When you take the average of something, what you do is you sum up how many things you have, and then you divide by the number of them. So, I could define an average that looks like this. I sum up the square of the things that I have and divide by the number. Now, this is called the sum of the square average. The mean square is what we say. So it's what happens when you take the average or the mean of the square of numbers. And what that means is that I can rewrite this right here as just v squared average times n. So this right here is v squared average times n. So now I have P on the left-hand side. And on the right-hand side, I have 1/3 the mass of one of these particles divided by the volume times v squared average times n. Now what I'm going to do is to move the v to the left-hand side. And I'd like to point out that one of the versions of the ideal gas law is that PV is equal to capital N times K sub B times T. And what I'm going to do is to plug this into this. That's on the left-hand side. On the right-hand side, I have 1/3 M times N times V squared average. Now, the ends cancel. I have a K sub B, T on the left-hand side. On the right-hand side, I have a 1/3 mass times the mean squared of the velocity. Now, at this time, usually what's done is we define the following. If I take this and I square root it, what I have is something called VRMS. It's almost the mean, almost the average velocity, but not quite. Because of the squaring process, it's been averaged out a little differently. So we just usually call this VRMS, or root mean squared. You take the mean of the square of something, and then you take the square root of it. So this is the same thing as 1/3 MVRMS squared. The next thing I'd like to do is to multiply both sides by 3 and then divide both sides by 2. On the left-hand side, that gives me a 3/2 K sub B T. And on the right-hand side, multiplying it by 3 gets rid of the 1/3, and that puts a 1/2 out in front. And now you have an expression for the kinetic theory of temperature. Temperature is related to the average kinetic energy of the atoms and molecules that make something up. That's what that says. Now, to work an example, what I'd like to know is what the RMS speed of a hydrogen atom at the sun's surface is. Excuse me. Now, so we're looking at an individual hydrogen atom, not a molecule. If you look stuff up, what you'll see is that you're given that the mass of a hydrogen atom, or a molecule rather, or an atom actually, I take that back, not a molecule, is 1 U, or 1.66 times 10 to the minus 27th kilograms. Now, you'll also discover that the temperature at the surface of the sun is about 5,800 Kelvin. What I'd like to find is VRMS. And I have an equation for that. 3/2 K sub B times T is equal to 1/2 mVRMS squared. So all I'm doing is just solving for this. I'm going to go ahead and get rid of the halves there. If I solve for VRMS, that is going to be the square root of 3 K sub B times T divided by M. So VRMS is equal to the square root of 3 times. Now let's see, Boltzmann's constant was 1.38 times 10 to the minus 23rd joules per Kelvin. The temperature is 5,800 Kelvin. And the mass is 1.66 times 10 to the minus 27th kilograms. So, if I solve for this, see the square root of 3 times 1.38 times 10 to the minus 23rd times 5,800, and then I'm going to divide that by 1.66 times 10 to the minus 27th. I get 12,027 meters per second. Now, it's this right here that in part powers something that we call the solar wind. There's this constant outgassing of material from the sun. It's made out of hydrogen. There's some helium nuclei and some other stuff. And this is one of the reasons why. Because you're going to see some of the particles leaving like this. Okay? If you think of this as the surface. Random motion says some are going to be going this way, some are going to be going this way, some this way. But then you're going to have some that directly leave out. And that in part is one of the reasons why you see it. Okay, so that's it for this particular lecture. In the next lecture, I'm going to talk about what do you do when your gas is not ideal, and introduce an equation called the van der Waal equation. Okay, and I'm also going to talk about something called the mean free path. And I'll see you then.